recording just for providing the videos to you. Okay, and then screen sharing, because otherwise in the video you don't see the slides. 1 second. Okay. Here we are. Okay, let's go to lecture notes for Harbour Engineering. Here we are. And let me go back to port planning and environmental impact, because when I closed the last lecture, I left untreated the part on energy from the sea and recovery of contaminated muds. Energy from the sea, there is not much to say because Professor Archetti is going to talk to you. I'm not opening the PowerPoint because I just need to talk 5 minutes, and we can refer to the figures that you can see here. So Professor Archetti is going to discuss it with you. And I mentioned to you that one possibility is to use the movement of waves in open sea, like maybe this installation here. And it is frequently applied in the former platforms for oil extraction. There are many of them, for instance, in the Adriatic Sea, which are now not used anymore. So a relevant question, also from the point of view of the environmental impact, is how to manage, what to do with these dismissed platforms. Some of them are removed. However, also removal is a delicate operation, because if you remove a platform, you destroy a microenvironment that has been created by the fisheries, by other living organisms like corals in the vicinity of the platform and over the piles. There is a lot of hosting environment for fisheries, etc. In fact, people that are passionate of underwater fishery, they like to visit these platforms because there is they find there a lot of fish. And if you remove these platforms, you originate turbidity, a plume of turbidity, because of course removing the piles, etc., we originate turbidity in the water, which is really damaging for the ecosystem, because turbidity, as you know, it's dangerous. It's impacting on the living organisms. So it is a relevant question, what to do with these platforms. And one possible solution is tourism. Indeed, they bring tourists to visit them because they can practice fishery, etc. Another possibility is to use them for production of energy, electricity, as wind, as energy farms, wave farms, actually. And so the way energy is produced is you put a floating body over the sea. The floating body is typically fixed to the platform, so they go up and down, and the floating part of it goes up and down. And the part that is fixed to the platform can host a turbine or whatever generator we decide to put there. So with the movement up and down, we can produce energy. As I said, this is an interesting opportunity. On the other hand, like other forms of renewable energy, it's intermittent. It's not constant. We cannot regulate it. We have to take the energy from waves when there are waves, when the energy is available. Like other forms, like wind energy, solar energy, unfortunately, they are not continuous. And therefore, it is an interesting source of energy, but we have to couple it with other forms of energy production that may compensate the gap. This is a general need, a general challenge for renewable energy production. We need to get energy supply from different sources which can compensate each other. Unfortunately, often when you have wave energy, you also have wind energy, because waves, as you know, are generated by wind, and therefore they cannot compensate well. Another possibility to use these platforms is indeed to use them as wind farms. So you can put the rotors, the wind rotors over the platform, and the wave floaters in the vicinity of the platform over the sea. So we can make a double use, multiple use of these platform for renewable energy production. In this case, as I said, there is little opportunity for compensation because usually, you know, when the sea is calm, typically you also don't have wind. Let's keep in mind that these another possibility is to use them as solar farms. So you put solar mirrors over the platform. And again, this is offers the opportunity to make some integration because you don't have you don't have solar energy during the night, but during the night you may have waves, and vice versa. During the day you have the solar energy, but you may not have the wave energy. So this offers a possibility for compensation. And an interesting feature of these solutions is that their environmental impact is maybe reduced with respect to analogous farms placed over the land, because over the land, of course, it's a different context. Usually, for instance, wind farms produce noise which over the land may be disturbing, may be impactful, and in the open sea is less impactful. And also in terms of landscape, of course, it's not nice when you see in the open sea platforms, but probably these farms have an impact over the landscape, which is reduced if you place them in the open sea. I mean, also the seascape is important, but an impact on the seascape is probably less relevant, at least in some contexts, as with respect to the impact on the landscape. So, I mean, it's important that you get an overview of these opportunities, because it is likely that you are involved for some reasons in the recovery or dismission of sea platforms. And the reason is clear, is that today, you know, oil is less popular with respect to the past, because oil means CO2 emissions, means an impact on climate, and therefore there is a push in order to use renewable energy instead of fossil fuels. And this is why it's not unlikely that you get an opportunity to this end. Let me spend a few words about the recovery of contaminated muds. This is another thing that you need to get some information from, and it's a problem that is more in the domain of biology, of sanitation, than in the domain of harbor engineering. But it is a fact that harbor management requires periodic dredging. Dredging means, I'm sure that you know, but let me just show you the link. Dredging means that you need to remove the muds, the sediments in the harbor area. We already talked a little bit last time about this. In the harbor area, it's a sheltered area, so turbidity typically gets settled down over the sea bottom, and you get an accumulation of mud. An accumulation that comes from the open sea, or it's eroded somewhere and comes into the harbor. And because the harbor is a calm, it's a quiet place, you have sedimentation. And therefore, periodically, because this mud, of course, decrease the depth of the harbor, you need a minimum depth in order to allow the sea to birth. And therefore, periodically, we need to remove these muds, and this is done almost in any harbor. It's an important operation that needs to be carefully planned. And let me just check if we have a link here on dredging. Yeah, dredging in harbor basins. So maybe that we discuss it later, so I don't spend much time now. What I just want to mention now is that these muds that you take from the bottom of the sea, I mentioned last time, they are contaminated. They are contaminated by several pollutants, and also some of them are natural. Think the organic substance, which if it is accumulated in a big amount causes the reduction of the concentration of dissolved oxygen in the water. You get a reduction of the dissolved oxygen because the decomposition of the organic matters requires absorbing oxygen. And therefore, you understand what is the impact. Less oxygen, deoxygenation means a reduced quality. And this is something that occurs also naturally, but in nature, usually the system is compensated. It's compensated because by definition, and through evolution, the natural systems tend to compensate. So basically, the water bodies in natural conditions, they can compensate, they can recover, they can destroy the organic matter because they have enough oxygen to survive. And this is due to the evolution. So only the ecosystems that through the years are sustainable, they survive. If we had through the years an ecosystem producing more organic matters than the capacity of the water body to degrade it, to recover from it, the ecosystem wouldn't survive. So the ecosystems that we have today have survived to evolution. So usually the natural systems are in equilibrium. But if we increase the content of the organic matter, for instance, because we create a sheltered area and therefore we have more accumulation, we have less oxygenation due to waves, because waves with the turbulence, they capture oxygen. In a sheltered area, you reduce oxygenation, and there might be conditions that favor the growth of algae, for instance, because there is some fertilizer that is brought by a sewer system. So there is a perturbation and the system may get not out of equilibrium, which means that water becomes without oxygen. And without oxygen, the degradation of the organic matters continues. This is not written here. It's just something that I would like you to know. The degradation of the organic matters continues, but in a anaerobic, with an anaerobic process. The anaerobic process, unfortunately, produces some pollutants, some byproducts of the anaerobic degradation are cause pollution. We don't go into the details. What I want to say is that periodically, this is the moral of the story, you need to dredge this area, and the result is a mud that is contaminated. And the displacement of this mud is a problem. This is a quote from Wikipedia. The proper management of contaminated sediments is a modern day issue of significant concern. Indeed, I fully agree. Because of a variety of maintenance activities, thousands of tons of contaminated sediments are dredged worldwide from commercial ports and other aquatic areas at high level of industrialization. Dredged material can be reused after appropriate decontamination. A variety of processes has been proposed and tested at different scales of application. Technology for environmental remediation. Once decontaminated, the material could well suit the building industry or could be used for beach nourishment. But unfortunately, decontamination, it's a costly process, extremely energy demanding in general. It depends on the decontamination process, but usually it's extremely demanding. And therefore, this is a modern issue. And I think I already told you that the Port of Ravenna, when we designed the Port Authority of Ravenna, when we planned the courses of this degree program, they suggested please include something on decontamination, mud disposal, because we have this problem. And they have indeed a lot of dredged material and they need to displace it. And, it's not easy to convince the population to accept that the dredged material is displaced through landfill. Landfill today, which means that you put any garbage into a land area and then you leave it there, you cover it with vegetation, and landfill is a practice that has been widely used for garbage displacement. Today, there is some resistance by the population to accept these landfill sites because they produce some smelling, they produce gases as byproducts. They are to some extent a little bit dangerous because, of course, they are realized by taking any care that groundwater is not contaminated. But you understand, when you put contaminated mud over the land, there is this risk. So you have to make the bottom impervious so that there is no leakage. And of course, we take any care. There are procedures that are well consolidated, well tested. On the other hand, there is a residual risk that remains. It's like for any human intervention, even for bridges, for dams, there is a residual risk. Even if we improved our knowledge, even if we improved our design methods, our projects, still, there is some residual risk. Okay, perfect. So I think we can close this very narrative lecture on port planning and environmental impact. This is just, yeah, please. Yeah, you asked the time for dredging, correct? Yeah. Because, yeah, perfect. They monitor regularly the depth of the harbor. They are required to do that. The Port Authority is required by law to monitor the evolution of the sea bottom. And also they are required to test the quality of the mud periodically, because they should take any care to avoid that contaminated material is released into the mud. So they are required periodically to test it. So they make samples and they bring them to the lab, and they are required to test the content of selected substances for which thresholds are set. And when they realize that the depth of the sea is decreased below a certain threshold, they are required to do that. I think there are more details in the lecture that I linked here, and I just want to anticipate. I think we will have time to look at it, but basically there is sediment dynamics modeling. In some cases, they are also required to model the dynamics of sediments. And I think there is something here, monitoring and dredging planning. And it's narrative, but if you're interested, you can read here. But I think we will have time to discuss it. Okay, now, if you don't have any question, do you have any more questions? Thank you for the question, by the way, I appreciate it. Yeah. The website for each one, is it? Sorry, say again. At the end of the website, you said a summary. Yeah. For some of them, yes. For other, not. For port planning and environmental impact, I think there is. But as I mentioned to you already, don't use it for studying. And this is my suggestion, because the PowerPoint is a synthesis. And yeah, okay. But if you think, for instance, you may use the PowerPoint for refreshing your mind. And my suggestion is to set the basis of the foundation of your knowledge, also for the exam, read the lecture notes. And then maybe if you want to refresh them, look at the PowerPoint by keeping into account that it doesn't tell you everything you need for the exam, but more importantly for your background, And in case of forcing estimation, I think there is the PowerPoint. Let me see. Yeah, let me download it. And good. And this lecture on forcing estimation is more quantitative, is more numerical, more mathematical, not heavy mathematics, not heavy math. But on the other hand, I want to anticipate. I try to mix the lectures that are basing on a narrative and the lectures that are more quantitative. This one is more quantitative. I anticipate that I will need to refresh to you some concepts of probability today, which usually students don't like. But on the other hand, probability, some knowledge of probability is extremely important for dealing with the drivers and the forcings in Harbour engineering. Waves, you know, it's a random process. I want to anticipate that in the second part, after, again, I will need to make only 15 minutes break. I'm sorry, they are making some repair works in the railway line, and therefore I need to take the train at 4:32, which means that I need to close at 4:10. So I will go on for 1 more hour. 2:30, and then 2:45, 4:15, something like this, okay? And in the second part, in the second hour and a half, I will go back to some introduction to R. Also today, I would like to introduce in parallel some notions of Python. I will explain to you why, but really, I think you may benefit a lot from these skills, and I want to offer you an opportunity, and we have time to do that. Okay, so let's focus on forcing estimation. And let me just get also the web page here. It's here because I wanna keep the web page at hand because there are several things that are not included in the PowerPoint, and I wanna make sure that I don't forget anything. Just 1 second here. So we need to discuss a variety of forcings. We will limit ourselves to a selection of them. And first, we limit ourselves to the study of the forcing from the sea. And we are not studying the forcing from the land. These forcings are usually dealt with in geotechnical engineering. And so we will limit our attention to forcing from the sea. And over the land, there are also forcings that may come from transportation. And the computation of these forcings is in the domain of transportation engineering. I just want that you get aware that the topic is extremely diverse. There are a lot of forcings to be considered. If you look at the port handbook, you will see that there is an extensive treatment of forcing. I think that focusing on the forcings from the sea is a good solution to get the concept. And I also think that we need to make this treatment because while transportation and the geotechnics, you take some notions from other subjects. In the case of the forcing from the sea, I think this is a unique opportunity to study them. And what we do usually, in general in Harbour engineering, is to use empirical formulas. This is something that makes the field from, on the one hand, more understandable, because empirical formulas do not require, their application does not require a deep knowledge of the theory. So on the one hand, it makes the field easier, it makes the treatment, the discussion easier, because you will see the formulas are not complicated. On the other hand, you know, these formulas, empirical formulas, have a lot of coefficients because empirism very frequently needs coefficients to correct the approximations that an empirical formula has to make. So the result is that these relationships cannot be easily derived through a mathematical development. And they need to be stored somewhere, not in your memory because they are too many, as we will see. So you need to be aware that these formulas exist, and you need to resort to them anytime that you need them. I'm not pretending that you learn by memory this relationship. Only one. I will ask you one, or at most two. I will ask you to learn by memory. Unfortunately, if we want to be able to use these formulas without looking at a reference, we need to learn them by memory. We don't have a mathematical development, a theoretical development that may drive us to derive them, okay? And another limitations of the empirical formulas, as I said, there are coefficients. So one problem with coefficient is to remember them. And for this reason, I say it's not needed. But another problem of coefficients is that they are context-based, meaning that they usually are estimated. The value of the coefficient is derived by looking at practical experiment, at practical evidence. So typically, when you need to introduce an empirical coefficient means a correction for uncertainty. So what you do is to look at data. And these data are collected in sites, in experimental sites. They may be collected in the lab, which is a type of an experimental site. They may be collected in real-world contexts, which is nice because the real world is better than the lab in terms of proximity to what we have to do, proximity to our practical applications. On the other hand, these data are context specific and you will never cover everything with this data. So you have to be aware that an empirical formula can be applied in the context it has been derived from. So if I get an empirical formula for port design in the Adriatic Sea and I go to apply it in the Pacific Ocean, it's not a good move. So the empirical formula is representative of the context from which it was derived from. If you apply it out of context, you get uncertainty. So this is the downside of using empirical formulas. And why we don't have a theoretical development for our design. In some cases, there is a theoretical development. But the reason why there is, it's not easy to apply a theoretical approach in Harbour engineering is precisely the presence of randomness, random processes. So the forcing given by waves. Waves are originated by wind, by weather. It's much different from the forcing given by a transportation, by a truck. So the forcing originated by traffic can be computed. Or in structural mechanics, the forcing given by the self-weight of a building or the forcing given by people inside the building can be quantified with a theoretical approach, because you know the max capacity, you know the behavior of this type of load. Here, you know, to describe with physical formulation the movement of waves, how they are originated, is complicated. So this is very context specific. A similar approach, to give you an idea, is followed in beach hydrodynamics and morphodynamics, which describes the movement of sediments caused by the sea, the displacement of sediments. Even if this is a movement of physical bodies, so we could apply the laws of physics to describe it. Actually, what we apply is empirical formulations. So we make measurements of movement of sediment, and then we try to fit these measurements with a formula, with an analytical relationship. And because it's so random, the process, it's so chaotic. Chaotic means that when you try to model it, if you make even a small mistake in the definition of the input data, the result changes completely. This means chaos, okay? And so it's so chaotic, so uncertain that we prefer a direct fitting of the data. We prefer what is called an inductive approach, as opposed to the deductive approach when you start from the theory. Deductive approach is I start from the knowledge of the theory, I build a model, and then I perform my task. And the inductive approach is I look at the outcome, I fit the outcome with an empirical model, and then I do my task. So we will work with empirical formulation, and this is something that occurs frequently in Harbour engineering. In other fields related to environment is a slightly different situation. If I think at my field, which is water cycle hydrology, there is a mix. And for some processes, like sediment transport in rivers, we use empirical formulas. But for describing the movement of water into a river, we use physically based models. We use the laws of physics, because this is something that is subjected to some uncertainty, but it is observable. We have a lot of data. There is less chaos. In the movement of water into a river, it's different than the movement of water into the ocean, where we have a lot of turbulence, we have a lot of chaos. So in hydrology, it's not like that. I tell this, I make this consideration, and I want to share this consideration with you, because I noticed when I got into the field of ocean engineering, harbor engineering, that the approaches looked to me more empirical with respect to what is I was used for other branches of engineering, and this is normal. What we do in design, in engineering design, is to operate on extreme conditions. This is clear. We need to design, to size the bollards, the mooring lines, the berth, by referring to extreme conditions, which are usually quantified, as I said, by using observations. First, before I move forward, I want to give to you an information which I think is useful. Let me go to the web page, because it's more complete there. And here there is a link to the glossary of nautical terms. If you need, if there is any, it's on Wikipedia, if there is any term in harbor engineering, ocean engineering, you are not aware of, any term that you wonder what is the meaning, of course you can Google it. But I think this glossary gives to you a very nice overview. Of course, you don't have to read everything here, but it's, I tell you, to prepare my lectures, I used this glossary a lot, okay? And for instance, what is the beam? Let's see, what is the beam? Beam. Here you see the width of a vessel at its widest point, or a point alongside the ship at the midpoint of its length. This is the beam. There is a link here, and if you click on the link, you get a picture, which is the picture that is included in my web page. And you see here, and there is, sorry, I closed the window, just 1 second. Beam. And there is also search, I think, in the glossary somewhere. Okay, let me find the beam. Beam. It was down here. Okay, good. Let me just see. So you see also an extended description, typical values, and I think, as I said, it's also important that you learn some orders of magnitude, and I think you have an idea of the width of a ship, of a huge ship, but still, I think you can find some useful information here. Okay, and another thing, given that we are in the B, another thing that we will use, ballast. What is the ballast? Is dense material used as a weight to provide stability to a vehicle or a structure, and it is widely used in ships. They have usually a tank. You see, this is a cross section of a vessel, and they have a tank that they can fill with water. And typically, they fill the tank when the ship is empty, because it becomes dangerous if the ship is designed to navigate with the full load. Of course, the ship should float over the water, cannot sink. This means that when you unload the ship moves up, therefore becomes more exposed to wind and less stable. And therefore, what we do is to load the ballast, to load the water in this tank to compensate for the unloading. This is extremely important. And we will talk about wind forcing over the side of a ship. You understand that if the ship is loaded, you have less side surface exposed to wind, and therefore it's less dangerous. The most risky situation is when the ship is unloaded. And maybe we say that it's in ballast. When it is unloaded, the ship, we say it's in ballast, meaning that the ship has loaded ballast to be stable. But still, a ship in ballast usually is less stable than a ship that is loaded, because even if you load the water, the tank cannot be huge, because otherwise you lose space for the load, for the stuff to be transported. So when the ship is unloaded, is empty, even if it's in ballast, it's less stable than when it's loaded, and people who navigate are aware of it. Okay. Yeah. Usually not. Usually not, because ballast. Because if you put usually ships are designed in a way that they are stable when they are loaded and when they are in ballast. This means that if you load the ship when it is in ballast, there is the risk that the ship sinks. So the ship, of course, has a navigation line that shouldn't be exceeded, which means, you know, I don't know how to say in English, but it's the level of water on the side of the ship when the ship navigates. And this cannot be very high, should be like a reserve, let's say. But when you unload the ship, usually, of course, the navigation line, the water line goes down. And we will see the nautical term. So usually when the ship is in ballast, it's not loaded. And when it's loaded, it's not in ballast. Because if you put both of them, I think it is dangerous, not for the equilibrium, but for sinking, you know. Okay, so what I wanted to say, so this glossary is useful, and in particular, we need to learn the terms that we use to indicate the size of a ship. So the beam is a term that we use frequently. Beam is the width of the ship. It's usually measured at the level of the waterline. The waterline is the level of water the ship is designed for when it navigates. So for sure, the waterline, the level of the waterline is not fixed. We assume that it's at the level of the ship fully loaded, without ballast and fully loaded. So at the level of the waterline, usually we measure the beam, but there might be different conventions. As you have seen in the glossary, in some definitions, they define the beam as the width of the ship, the max width of the ship at mid-distance between stern and bow. Stern is the rear of the ship, and bow is the frontal part of the ship. Okay. And so there are different definitions of what is the width of a ship, depending on the regulation. And what you see here on Wikipedia is the one that is more internationally accepted. Anyway, the beam is the width of the ship. Okay, whatever we measure it, there is not much difference between one definition and the other. And the draft D is the distance between the waterline and the bottom of the ship. This is called the draft. And then there is the freeboard F. The freeboard is the distance between the deck of the ship and the waterline. Okay. In terms of length, there is the length overall, and OA here. You can see on the graph what is the length overall, is the max length overall. Okay. And then there is the length at the waterline length is WL, measured over the waterline. And there is the length between perpendiculars, and we refer, as you see here, it's PP. So you see on the sketch how it is measured. It's not much used, and basically it is used to indicate the length of the bottom of the ship, to give an idea of the length of the bottom, which is different from the length overall. The length overall is larger, and also the waterline length is larger. Okay. These are some terms that we will use, in particular the beam, the draft, and the freeboard. Now, let's focus on the loads then, and the forcings that we need to use to estimate, to design berths. And let's start from the mooring loads. So, what is a mooring load? When a ship is berthed, is docked, it is connected to the berth, to the land, through the mooring lines, the ropes, the big ropes that you see are used in order to keep the position of the boat more or less fixed. It's not really fixed. There is some flexibility because, you know, the ocean is moving up and down, and can move also for wind gusts. Wind gusts are the shocks, the wind shocks. And we need some elasticity, because if the mooring lines were not elastic, the forces over the mooring lines would be higher. So we need some elasticity. The mooring lines, the ropes, look static. Actually, they have some elasticity. And given that they are very long, this elasticity means that even when it is docked, the ship can move a little bit. And we feel it. When we are over a moored ship, we feel that there is some movement up and down, but also some movement in the horizontal plane, which is due to this elasticity. Okay, and so the mooring lines give some load to the mooring points and therefore the berth, and this load is originated by different sources. It can be originated by wind, and it's wind that is impacting the ship. It's not impacting directly the berth, because, you know, the surface of the berth, the area, the side area of the berth is nothing with respect to the side area of a ship. You understand? There is a huge side surface in a ship, and in fact, people know that the side wind is the most relevant driver, because there is an extended surface of the ship along its longitudinal direction. So wind can originate a relevant forcing, wind through the ships and through the mooring lines. And then there are waves which can generate forcing again over the ship. All of these three forcing that I'm mentioning are forcing over the ship. But when the ship is berthed, is docked, these forcings are transmitted to the mooring points and therefore the berth, and also the currents. You understand that waves can generate a relevant forcing more than currents, but even currents, depending on the conditions, depending on how protected the harbor is, can generate a significant forcing. We will not consider the loads that are originated during berthing. And these loads are due to the transfer of through the mooring lines of the kinetic energy of the boat. You understand that? I go back to the PowerPoint, just 1 second. You understand that when it's not here, the presentation, it's here. When a ship is berthing, is approaching the dock, then what we do usually, of course, we minimize the velocity, but in order to stop the ship, usually what we do is to throw a mooring line over the mooring points, and there are people there who fix the mooring line to the mooring point, and therefore, when the mooring point gets tension, when the mooring line gets tensioned, the ship is arrested. It doesn't move anymore, which means that there is a forcing, a temporary forcing over the mooring point. And another issue is the impact of the ship. Typically, we put fenders in order to protect the berths against these impacts, but through the fender we get, when the ship is impacting the berth, which is unavoidable, it's almost unavoidable, especially if the sea conditions are a bit turbulent, it's unavoidable, and therefore you get a kind of shock due to the impact of the ship against the berth. We will not consider this. If you look at the Port Designer Handbook, there are empirical formulas that allow you to estimate. And for the case of, to estimate these loads, for the case of the kinetic energy, you may also have some physical basis there, because it's quite easy. If you assume that the ship is berthing with a given velocity, it's relatively easy to estimate by making conservation of energy. It's relatively easy to estimate the shock, the forcing, the mooring lines transmit to the mooring point. But usually they are mainly empirical formulas, and the reason why I'm not treating them is that I think it is useless that I give to you a huge set of empirical formulas. I don't find it useful. So we don't treat them. And if in the future you need to estimate these temporary berthing loads, you just have to look at some references and you get empirical formulation. There might be also unexpected events and accidental event, what we call extreme loads, maybe because the ship is making a mistake, a maneuvering mistake, and there is a strong relevant impact. So we need also to take into account these unexpected events. Okay, so let's concentrate on wind. And first of all, I want to give you some orders of magnitude. And the order of magnitude is related to the computation of the mooring loads. So you get an idea of what is the range of load we should expect. As you can read here, for ships up to 20,000 tons displacement, which means overall weight, and including the load. And each mooring point is expected to receive an horizontal pull ranging from 10 to 100 tons. Depending, from 10 to 100, there is a huge range. So what is governing the variability within this range? The ship displacement, the type of load, etc. And in terms of vertical pulls, we take usually half of the horizontal pull, acting at the same time. Okay, acting at the same time. These are orders of magnitude. And as you can read there in the last line, pull load should be considered occurring shipward. So basically it's attraction, seaward, it's attraction at any angle with the berthing front, because we have to select the less favorable condition. we will see that the mooring lines are oriented with respect to the direction of the berth at an angle. They are not only perpendicular. Sometimes they are displaced also almost along the longitudinal line. And therefore, we have to select the worst condition. And I can show you a sketch of a mooring line, of mooring lines. So first of all, let's see if on Google we find something, sketch mooring lines. There is something on my web pages, but I take the opportunity to see if there is something more. Okay, this is interesting. Yeah, let's see this because it's a perspective. So these are the mooring lines, and let me visit it. This is copyrighted, so I cannot include it in my web page, but sometimes there are copyrighted figures that are really interesting. So this is, you see the term, the stern, the bow, what we call in Italian poppa, and the bow, it's the prua, it's the front part of the ship. And here you see typically the displacement of the mooring lines. Sometimes you also see for very long ships, mooring lines midway, close to the mid of the ship. But usually what you need is a mooring line, at least 6 mooring lines for a ship with a significant length. Of course, if you berth with a small personal boat, you can make a safe berth with 2 mooring lines. But usually you need to moor the ship, in any case, irrespective of the size, with at least 2 mooring lines at the stern and the bow. And if the ship is important, you need at both stern and bow 3 mooring lines. One, here the numbers 2 and 5 that are almost perpendicular to the berth, and the other ones here 4 and 6, for instance, which are oriented at an angle. They are not perpendicular, and the 2 directions are opposite direction. So the perpendicular mooring line serves the purpose of keeping the boat close to the berth, so that the boat is touching the berth. The mooring line placed at an angle, basically they impede the movement of the boat along the longitudinal direction, because if you think of a situation here where you remove the mooring lines number 1, 3, 4, and 6, with only 2 mooring lines perpendicular, the ship could move forward or backward, because the perpendicular doesn't provide a good anchorage for the movement along the longitudinal direction for the direction of the berth. So you need these other mooring lines placed at an angle. Okay, and also this is interesting, but we will see these terminologies. And for the mooring lines, they have a name, and the people working in navigation, they know these names quite well, and we will see the detail later. Okay, I will try also to simplify it. Okay, so these are the orders of magnitude of the pools. So again, 20,000 tons displacement, which is the displacement of a ship of mid-size, can originate a horizontal pool ranging from 10 to 100 tons, and an horizontal pool that is half of a vertical pool that is half of the horizontal pool. We will see how to compute these loads along the mooring lines in detail, but the orders of magnitude are important, and try to remember them also for the exam, okay? Okay, oops, sorry. Okay, now, if the design ship is more than 20,000 tons displacement, the assessment of the mooring loads should be carried out by considering all possible forcings operated at the same time. And this is a guideline that is given by the Spanish standard. I think, why Spanish? Because it is one nice example of national regulation that is quite updated, used also at the international level. As I mentioned to you, not all the countries have regulations in place for the design of harbors. This is a nice example, you know. Of course, Spain has a lot of a great extension of coasts like Italy, and this one is a relevant reference, and it's public domain. This is another thing that suggested me to put it here. Of course, when you apply it out of context, you have to make sure that you don't have, as I already told you, specific regulations and guidelines for the country where you are working on. Okay. Okay, so wind forces. Wind forces originate pressures over the body of the ship, and they are a relevant forcing. They produce an important portion of the mooring forces. And wind forces, in fact, are generally more relevant with respect to forcings originated by currents and waves. And therefore, their computation is important and gets a lot of attention. If you want to describe wind forces, you need to know what kind of wind you may expect. And wind is characterized statistically. So wind is not characterized by using atmospheric models, physical models. And for practical technical application, we characterize the wind with statistics. What we do is to make wind measurements. And we hope that we also have measurements in extreme conditions. So we need to have an extended record. And therefore, what we need to do is to make sure that the record, we have a sufficient set of data. The way we characterize the wind forces, the way we present them, the way we present the result of the statistical analysis of wind measurements is through the wind rows. And why do we need to have a particular tool to present, to characterize the wind forces? The reason is that wind, it's not only a matter of wind velocity. To characterize wind, we need to specify velocity and direction. So it's not like measuring, it's like for waves. For waves, you have to measure wave height and direction. And the same for wind. It's not, for instance, for rainfall, we just need to give a number. It's rainfall, that's it. And you don't have to give additional information. And for wind, you need to characterize, as I said, velocity and direction. And therefore, we need a way of delivering the information that is efficient. I mean, a way to present the information, the statistical information. The wind rows is nothing else than a way to present our measurement in an understandable manner, in a very efficient manner, and it's used internationally. First, I think I have a slide. Let me check. Yeah, on the wind rows. But before looking at the wind rows, let's focus a little bit on how the data are collected. Wind is measured through an instrument called anemometer. And the anemometer measures the velocity and the direction. Okay. anemometer. Let's take again Google and let's look for anemometer. So let's see some images. And okay, here. This is a nice example. This is a nice example. You see here, you have the instrument on the left, on your left here, which is called, it's rotating, measuring the velocity. The instrument on the right is measuring the direction. And you see the two cables, they bring the data, they are measuring continuously, and they bring the data to a transmitter, and we get the data in real time. This is a typical example of an anemometer, and there are simpler instruments which can put the two sensors together. So they are not always separated. It is very easy to measure the wind velocity, and this is a lucky situation. If you think, for instance, of rainfall, it's not so easy. The anemometer is a very simple instrument, and it is also incorporated very often in let's say, portable weather stations or domestic weather stations. You see, you may know that several people who are passionate of monitoring weather can install a weather station in their home, and wind is a variable that is easily measured. On the other hand, you have to respect some protocols in order to consider the measurement reliable. For instance, you have to make sure that you don't have any screen around that is slowing the wind down. So this must be placed in an open space, typically over a roof. And typically, the recommendation is that for a rigorous measurement and for comparability of the measurement, the requirement is that it's placed at 10 meters over the ground, at an height of 10 meters over the ground. And then it is required that there are no buildings around. There must be an open space with some minimum size, which is recommended by protocols. What is important is that we remember the 10 meters requirement. Another feature of the wind that you have to take into account is that the velocity of the wind is rapidly changing. We know that, okay? Especially in extreme conditions, you get kind of what I call gusts, meaning you have some short time periods of high velocity followed by a slowing of the wind velocity. And you have this kind of shocks, and they are called gusts. And typically they last for a few seconds only. So it is important that when you report a measurement of wind, you also report the length of the time window during which the wind was measured and averaged on. So for instance, some scales that we will see for wind classification are based on the velocity of the wind measured at 10 meters over the ground and averaged over a duration of 10 minutes. In this way, you average out the gusts, the very short gusts. On the other hand, there are some design recommendations that make reference to the wind velocity for a gust of 30 seconds, which means that you average over 30 seconds, because you want to make sure that even for very short gusts, we are safe. Okay, so measurement of wind through the anemometer at 10 meters height over the ground, and averaged over a duration that is varying and is recommended by the rules and the design requirements. And we use this data for elaborating the windrows. So you have to specify, this is the windrows which was taken at the anemometer of LaGuardia, as we will see, LaGuardia Airport, as we will see. I have an example from there for wind speed averaged with a duration of, usually people say, they don't say average, they say wind speed for a duration of 30 seconds or wind speed for a duration of 10 minutes. Okay, good. Now let's go again at our presentation so that we will look at LaGuardia. One more consideration. I already mentioned the length of the observation period. The longer, the better. Okay, so this is another thing that you have to know. So you get a wind rose. Okay, perfect. And what is the wind duration and what is the length of the observation period? The longer, the better. Okay. Say again. Sorry. The length of the observation period. Observation period means here there is mentioned as the length of the historical wind record. And you may ask me what is a good duration. I would say an observation period of 10 years is okay. Okay, and it's unlikely that you find observation periods longer than 30, 40 years. It's unlikely. Keep in mind that ocean engineering and harbor engineering, these disciplines, I mean, they have an age of less than 100 years. Okay. Okay, so this is the wind rose at LaGuardia Airport. Let me just look on the web to show you. If we go to Wikipedia, wind rose, we see precisely this figure. Of course, this is not a surprise to us, given that I need to put figures in my lecture notes that are public domain. Wikipedia is a great source. Okay, so wind rose plot for LaGuardia Airport. Let's see if we get more details here, because it's not specific. I can't see here wind duration source. Okay, let's see. The source should be here. Let's try to click here to see if they give more information. or service unavailable. Okay. You see that also Wikipedia sometimes has some broken links. Okay, and let me just check. Sorry. Let me just check here if it is specified here, the length of, because we are missing here the information on the length of the observation period and the duration of the wind, but I don't think it is specified here. In directional estimate. Okay. I don't think there is information here, so let's forget about it for this particular case, but let's focus on this graph. So what is the wind rose reporting? It's I try to be clear. It's a bit complicated. I think it is a very efficient way of representing it. I think that if you look at this graph, what is the first perception that you get? The first perception that I get is that the main direction of winds is the south direction, followed by the west direction and northeast direction. And southeast is probably the less prevailing. This is clear. Okay, that's fine. And another thing that comes to your eyes is that you have a circle at the center 3.6%, which represents the calm condition. And the calm condition is extended in any direction, of course. It's calm, it's no wind. So this circle should stay at the center of the windrows and should have the same extension in all directions. And 3.6%, it means that 3.6% of the time we have calm conditions. Calm is usually defined with a velocity of less than 0.1 meters per second. There is a threshold, okay? Because of course, strictly speaking, it's never calm. But there is a minimum velocity of the wind such that the anemometer doesn't rotate. And so it's assumed as zero, okay? It's never zero, precisely zero, but we assume that below a certain threshold is zero. And then you have 1 hour in a day, on average, where you have calm conditions, and then you compute the percentage, 1/24, okay? And so you express it in percentage terms, and you give this percentage of calm conditions, okay? And percentage of time is analogous to frequency. It's the same thing, because it means that for 1/24, you have calm condition. It's a frequency, okay? I told you that, you know, it depends on the variability of the weather, but I would say that 10 years of measurements are enough. No, continuously for 10 years, they record, for instance, the 30-second wind velocity. So every 30 seconds, they make a measurement, and this is extended for 10 years. And then you get how many measurements, or let's simplify it. Let's suppose that they take measurement for 1 day, which is not representative, but let's take 1 day. And then every 30 seconds, you get the measurement. So in 1 day, you have 86,000 seconds. So if you divide by 30, it means that in 1 day, you get something like 3,000 measurements, okay, of 30 seconds. Yeah, no, the anemometer is rotating always rotating, but every 30 seconds, they take the average. Or some instruments, every 30 seconds, they get instantaneous measurement, and they assume it's the mean, okay? So basically, as I said, in a day, you have 86,000 seconds. Divided by 30, you get almost 3,000 observations. Of these 3,000, you may get 1,000 of zeros, and then you have calm conditions for 33%. If you get 100 zeros, it's 3-point-something%. And this is equivalent to frequency. By the way, let me anticipate that frequency is a synonym for probability. So we may say we have a probability of 3.6% of zero wind. Okay, frequency, keep it in mind, keep this consideration in mind. Frequency can be used as a synonym of probability. Okay, so 3.6 is a frequency of zero, and that's it. Now, let's now focus on a direction, because so far we focused on the zero. The zero has no direction. But when you get something greater than zero, it's a longer direction. Okay, so let's focus on the south direction, which is the easier to read because it's the longer one. So, and let's look at the legend on the right. The legend on the right, you see that there is calm, zero, 3.6%, okay? Perfect. And then there is a first range, which, by the way, is not shown in the windrows. You don't see the light blue nowhere, which is wind speed up to 1.54 meters per second. Okay, light blue is the range between 0 and 1.54 meters per second. And you see that there is a frequency of 0. There is no measurement within this range. You may say it's a bit strange because how can you pass from 0 to how can you skip a range? Okay. You know, maybe that indeed here there was an approximation. I don't have an explanation for this hypothetical question. I noticed myself that it's a bit strange. If you go at the next range, it's from 1.54 to 309 meters per second. Then you have a frequency within this range of measurements of 22.6%. Okay, so you may ask me, what is the percentage between 0, including 0, and 3.09? You have to take the sum. So if you ask me, what is the percentage of measurement between 0, including 0, and 3.09, I would say it's 22 plus 0.6% plus 3.6%, which means 25.2%, 26.2%. Next range, dark green, from 3.09 to 5.14. We have a frequency of 35% within this range. Next range, 27%. Next one, 6.1. Next one, it's the highest wind velocity, 15 meters per second. It's 1.6%. So you would expect that if we cover the whole range, if you take the sum of all of these percentages in the legend, you get 100. Indeed, you are very close to 100. It's not precisely 100 because maybe that they missed some observations, for instance, in the range where they put the 0. Okay, so there is, in this case, there is some approximation, but you get very close to 100. You see, 3.6 plus 22, you get to 26 more or less. 35 plus 26 is 61. 61 plus 28 is 89. 89 plus 6, it's 95. 95 plus 2 is 97. You are close to 100%, which is what you would expect. Okay. Indeed, I think there is some approximation here. Okay, but this is a picture. The legend gives to you a picture of the distribution of the wind velocity over all the directions. Now, if you are interested to look at one particular direction, the south one, along the south direction, you see the distribution that is given by the windrows. So you have 3.6% of 0. Okay, perfect. And then you have the blue range. You have a percentage of about 2%. The dark blue range, the light blue, it's absent, it's nowhere. The dark blue range, it has a percentage of about 2%. If you see, the circles are displaced at intervals of 2%. And the dark blue range in the south direction, this one, which I'm pointing with the mouse, it's extended up to 2%. Good. And then we have the dark green. The dark green is extended by 2% up to about 8%. So there is a 6% of distribution in this range. Okay. And then we have these two ranges. It's more or less the same color. You see, it's I would say light green plus a little bit darker green. These two distributions, these two ranges, allow us to reach a overall frequency along the south direction of wind of 12%. Now, if in the south direction, I have a wind that is registered 12% of the time, okay? My understanding is that if I sum the percentage over the overall directions, I should get 100. Let's try to make it. Here it's about 12% of the time in the south direction. Let's move clockwise. 4% of the time in this direction here. Look at my mouse. So 12 plus 4 is 16. Move to the next one. It's about 6%. We get to 22. 22 plus, let's say 4%, more or less, a little bit less, 26. 26 plus, say 8, 34. 34 plus 7, 41. 41 plus 10, 51. 51 plus 7, 58. 58 plus 6, 64. 64 plus 4, 68. 68 plus 8, 76. 76 plus 8, 84. Plus 3, 87, plus 1, 88, plus 2, 89, plus 3, 92. 92 plus 3.6, 96, 97. You see that we are getting close to 100. So basically, if I get the distribution of frequency over all the direction, I get to 100. If I get the distribution of frequency over the wind speed ranges, I get 100. So you understand that it's nice. I mean, it's efficient. If you are a seaman, you look, okay, let me see, in the west direction. In the west direction, I have 3.6% no wind, and I have quite a significant percentage of from 4% here to about 9% here. So 5% of the time, I have wind that is quite strong. Okay. In the south direction, it's the prevailing direction, but the prevailing velocity is not so high. And if I go in the west direction, I have a larger band of green color, of the light green color. And if I look at the most dangerous wind, which is the almost yellow band, it can be found only in west direction and in northwest direction and in northeast direction. It's not a high percentage, but still. So this is the windrows. There are several variants of this graph. Let me see where I looked for it. 1 second, windrows. It's here. So if we look for windrows and images, okay, windrows. There is also the musical. Okay, let's see. Let's search for windrows and let's see the images. If okay, there are some windroses and some images of music, but what we see is you see another one here, and this is windrows plot. Okay, windrows plot for Borger Atkinson, and observed between. Look here, observed between 1st of July 1996, 13th of September 2023, and then it's observation used 200,000, 233,000 more or less. Observed without wind, average speed, okay, and calm values are less than 2 miles per hour. And wind speed, here you have the legend. The only thing that I can't find here, but we could probably look at the website, is the duration of the wind. When you don't see any duration, it's likely to be 30 seconds, but we may try to visit the website if we are interested. But you see that the way of showing it is it's given by the National Weather Service, and you see the south direction is the, let me see, I don't see the wind duration. I'm trying to here you have a calm situation of 5.7. And the important thing, this is the variability of the windrows in the months, because this is an average over the year, but it's also important that you get the distribution over the months. And you see that there is a lot of variability. And still I can't find the duration of the wind measurement. I would say that, let me see if I get another example, because this is an example that, this is Climate.gov. This is Chicago Airport, I think. And let me see, wind speed, wind rows chart. Let me see if we can find it, the specification of the wind duration. Okay. Okay, this says that we can get, if you register to this website, which is climate.gov, it's a governmental site of the United States, and it's from the National Ocean and Atmospheric Administration. If you register, you can get the windrows for selected sites, and from particular course, I think you have to get into the website to get more information. The current hourly station information, maybe 1 hour, maybe that this is derived on data from 1 hour, and windrows from hourly data sets. Yes, this is a windrows from hourly data set. Hourly means that the duration is 1 hour of wind. And then when you have to make a project, you can introduce coefficients for getting the gust velocity. It's called gust coefficient, and it's typically 1.2. And when you have a measurement that is like 1 hour, from 10 minutes to 30 seconds is 1.2, sorry, it's 1.2. And from 1 hour, you have to look for if there are recommendations, but it is more or less the same order of magnitude. Okay, I am 6 minutes late with the break, so let's meet again at 10 to 3, okay? 10:09 to 3. Okay, let me close micro and web. Okay. We can continue. More or less, we understood then how we can get information on the wind velocity that we have to expect. And now we need to learn what kind of wind velocity we should use. Because, of course, here we have the full spectrum. Before I move forward with this, let me just show you. These next slides are explanations that I already gave to you on the computation, on the fact that the sum of the percentages should sum up to 100, etc. Now, what is this graph? What I wanted to tell you before moving forward is that through the windrows, you get percentages of ranges of wind velocity along a direction. These percentages, as I already said, are frequencies, and therefore they are synonyms of probabilities. If we put into a graph, for instance, along the south direction, the percentages, and we put the wind velocity in the horizontal axis, and the percentage of not exceedance over the vertical axis, what I mean is that what I'm reporting here is not, I go back to the graph of the windrows. What I'm reporting here along the south direction for each wind velocity is not the percentage of each range, it's the percentage of not exceedance. So basically, if I, as I said earlier, if I want to get the percentage of not exceedance of a velocity of 5.14, what I have to do is to sum 3.6 plus 0 plus 25, 22 plus 35. This is the percentage of not exceedance of 5.14. And this is an information that is useful because in some of the cases, you need to estimate the frequency of exceedance of a certain wind velocity. So I need to say, in this place, for 90% of the time, I have a wind velocity not exceeding 20 meters per second. And therefore, for 10% of the time, I have a wind velocity exceeding 20 meters per second. This is the kind of information that sometimes I need. Why I need this kind of information? Because there are some rules for design that tell you that you should take as the basis for your project a wind velocity corresponding to a given percentage of not exceedance or exceedance. It is the same thing. If you get the percentage of not exceedance, this is equivalent to the percentage of exceedance. Percentage of exceedance is equivalent to 100% minus percentage of not exceedance. Okay, so I write it here. So the percentage of exceedance is equal to 100% minus the percentage of not exceedance. Okay, clearly, it is very simple. So this is an information that sometimes we need to know. This is why I have drawn this graph. And this graph, look, the percentage is computed as a fraction of the wind speed over all the directions. So in the south direction, what is my total expected sum is about 15%, because this is the percentage of the wind that I get along the south direction with respect to the total. And therefore, this is what I find here. I start from 3.6%, and then I get close to 16% with a wind velocity of something a little bit lower than 12 meters per second. This distribution is a distribution of the percentage of not exceedance. If you want to get it in the range 0-100%, you just have to rescale it. Okay, and it's a plot that is useful because, as I said, it gives to you the percentage of knot exceedance along a given direction. One thing, the wind velocity may be expressed in meters per second or in knots. Usually in the marine terminology, they prefer to use knots for tradition to measure velocity. And the rate of transformation, so if we write here transformation, or let's say knots. Okay, so these are knots velocity. Sorry, it's knots to miles. Okay, knots to meters per second. Okay, you see, 1 meters per second is equivalent to 1.94 knots. Okay, and so the wind speed, sometimes you will find it expressed in knots, and roughly speaking, it's 1 knot is, 2 knots is 1 meters per second. You have to divide by 2, okay, roughly speaking. And if you want kilometers per hour or miles per hour, it's, you see that 1 knot is about 1.8 kilometers per hour, okay? Usually when you are involved in some navigation issues, they give you the velocity in knot, and usually the velocity of cruise ships is about 30 knots, which means, but they are already fast, which means 50, something like that, kilometers per hour. Okay, let's get back to the wind rows here. So this graph is useful. It gives the percentage of knot exceedance. And keep in mind that it's a synonym for probability. And sometimes, indeed, the rules tells you the probability of knot exceedance, tell you to make reference to the probability of knot exceedance rather than the frequency. Okay. Good. Now, before I give you some information about probability, let me move forward and say something related to, as I anticipated just a little bit earlier, to the kind of velocity that we have to use for our projects. So let's move forward and let's forget probability for now, because there are some slides focusing on probability. Why? I show you the web page. So in the web page, after the treatment of the wind rows, given that I introduced probability because I said it's a synonym of frequency, there is a box which describes probability, but let's forget it for now. And let's move forward with the wind classification. Why wind classification? Because we need to discuss what kind of wind velocity we have to take as a reference for our project. And with kind of wind velocity, I mean wind for a given duration, for a given condition, because it must be an extreme wind. And therefore, I want to introduce the wind classification. And I make reference to the Beaufort wind scale, which is an international standard. It was introduced a lot of time ago. I opened the Wikipedia page just to give you an historical perspective, and the scale was devised in 1805. So it's more than 200 years ago by Francis Beaufort, and he was an hydrographer. And the scale was different from the one that is used today. And also they changed the unit of measure, because today we tend to use a scale in meters per second rather than knots. And also today, the number of classes of wind classification has increased. Like any other classifications, this scale serves to get oriented into the type of wind conditions you may deal with and the type of wind conditions that you have to consider. Okay, this is a picture that is interesting. This is a ship in a force 12. It's an hurricane force at sea. And you see, this is the highest grade in the Beaufort scale. And you see the size of the waves. I will tell you something more about a visual understanding of what a kind of wind scale, a given class of wind scale means. Okay, so you see this is a huge ship, and you see the size of the waves. Okay, but I will show you more pictures. 1 second. Okay, let's go back to our scale, which is here. So you see on the horizontal axis, you have velocity in meters per second in the bottom and knots in the upper part, in the upper axis. You see more or less it's divided by 2. In knots, you take meters per second, you divide by 2, and you get the velocity in knots. And you see the 12 classes from calm to light air, light breeze, gentle breeze, moderate breeze, fresh breeze, strong breeze. So basically, you have calm, light air, breeze in 5 classes, and then the gale. The gale, you have 3 classes: near gale, gale, strong gale, and then you get another class that is the storms, storm and violent storm, and finally the hurricane. So you see, hurricane corresponds to a velocity of the wind of 35 meters per second. So you get the meaning. It means 65 knots, which means more or less 130 kilometers per hour. So to give you an idea, with a wind velocity of about 60 kilometers per hour, it's difficult to walk. It's difficult to walk. When you get the gust, it's difficult to walk in such a velocity. With 130 kilometers per hour, it's impossible to walk. It's really a strong wind. You understand what it may be. I'm not sure if you tried with a motorbike to run at a speed of 130, but you understand it's a very strong pressure. Okay, and to give you an idea of the order of magnitude, the breezes they vary from the light breeze is about 10 kilometers per hour of wind. The strong breeze is about 50 kilometers per hour. 50 kilometers per hour is quite strong. You can still walk. You can still walk. I mean, even if with 60, you can still walk. But I mean, with a wind speed that exceeds 50 kilometers per hour, it becomes a bit. But let's say that the breeze is something that you can really stand with no problems. The gale, the strong gale, is 90 kilometers per hour. It's tough. It's really tough. And it may happen also to experience winds like these. In the flat areas is difficult. In the mountains, it may happen. 100 kilometers per hour in the mountains is quite frequent. And the storm, it's something that exceeds 100 kilometers per hour. The violent storm is 120, and the hurricane is more than 130. Okay, so just to give you an idea of the type of conditions. And another thing that you have to remember, which I introduced a while ago, is the gust factor. So the ratio between a peak wind gust, a peak wind velocity, and the mean wind speed over a given period of time. So when you only have measurements of average speed over a time interval, typically maybe 1 hour, typically or 10 minutes, and you are required to refer to a gust conditions, which means something like 30 seconds, you need to use the gust factor. And as I said, it's about 1.2, we will see. What I suggest you to learn is not the name of any of these 13 scales, but just at least the main terms that I mentioned to you. So the breeze, the gale, the storm, and the hurricane, in order to get acquainted with the terminology. Okay, this is perfect. Another, we already talked about the ballast, so let's forget it, or not let's forget, let's skip this slide. And it is important that I introduce the ballast at this stage, because as you will see, you have to refer to ballast conditions when you compute wind forces, because it's the most unfavorable condition. So if you get a ship that is moored, it's docked in ballast, the windage area is the max possible. And therefore, this is the condition that you have to adopt, okay? So to estimate wind forces, again, national standard and regulations you should refer to. And I will show you empirical formula, which is taken by international standards. And the basic design variable is, of course, the wind velocity, because as you will see, the wind forcing depends on the area of the ship, depends on other direction of wind, but the first and the main design variable is the wind velocity, which we estimate from the wind rows. But let's keep in mind, according to these international standards, that the design wind velocity, we call it capital V with the subscript W, velocity of wind, should correspond to the max velocity of the gust that we need to consider. And typically, as I said, we use the 30-second gust. And it's about 20% higher than the average wind velocity over a 10-minute period. Why 10 minutes? Because several measurements are taken by referring to this duration. Of course, if the average is computed over 1 hour, you have to increase the gust factor for the same duration of the gust, 30 seconds. You have to increase it. So it will not be 1.2, it will be something like 1.4. The increase is not so relevant, but you have to consider it. The only indication that I give to you is 10 minutes to 30 seconds is 1.2, as several international regulations suggest. But you may have tables, you can find on the web the tables of the value of the gust factor depending on the duration of the gust and the duration of the averaging period. Okay, so I make reference to the Spanish standard here, okay? And first of all, what is the recommendation for the order of magnitude? The recommendation is, in absence of more detailed information on wind speed, the recommendation is to adopt a minimum wind velocity of 22 meters per second with a gust factor of 1.2. Okay, this is the mean recommendation. Basically, they say if you don't have any measurement, the minimum wind velocity that you should take is 22 meters per second. The same rules suggest for normal conditions and mooring operations, because we also we also need to know the forcing during the mooring operations. So we assume that mooring operations in normal conditions take place. Normal condition means not with an extreme wind velocity. We are avoiding to moor ships when there is a storm. We wait for it before mooring. In some cases, if a ship is moored and we get a storm, an emergency solution is to undock the ship, so to release the mooring lines and let the ship get into the sea, because in this way you reduce the forcing on the berth, you eliminate the forcing on the berth. And so this is why we don't refer to extreme conditions for computing mooring forces. For docking, the rules suggest to adopt a minimum wind velocity of 17, which is lower than 22. 22 is the situation, the minimum situation that we should refer to for a moored ship. When mooring, the extreme situation is less intensive. Why? Because we avoid to moor if the wind velocity to dock, to approach the berth, if the wind velocity is so large. There is also, you know, when docking with a strong wind, there is the risk of a strong impact between the ship and the berth. So basically, for mooring operations, 17. Other standards, other international standards suggest a minimum velocity of 30 meters per second. So the Spanish one suggests 22. Other standards say 30. It depends also, you know, the Spanish standard refers mainly to the Mediterranean. It depends on the type of sea, on the condition that you may predict that are more likely to occur. And on the other hand, as you can see in the bottom of the slide, it is not recommended to exceed a wind velocity of 40 meters per second for calculating mooring forces, because in some cases, if we get to so extreme situation, the ship would normally either leave the berth or take in ballast to reduce its wind area. So it means that if we really get in a difficult situation, we have two options: unberth, so leave the berth, or taking additional ballast, additional load into the ship in order to minimize the windage area. And therefore, I mean, wind velocities for computing mooring forces above 30 meters per second usually are not considered. 30 meters per second is considered enough conservative, enough precautionary. Okay, but once that we know the wind velocity, how can we compute the wind forces? And here we get to this empirical formulation, which I suggest you to learn by memory. And to help you learning it, I write it on the blackboard. Let me check. Here it is. Okay, let me use the same symbols. So this is, we call the wind force in PW. So this is the total force of the wind against the ship. It's not a mooring force yet, okay? This is the total wind force over the ship. And then we have subsequently, later on, to split it along the mooring lines, okay? This is the total. So first of all, we get a coefficient CW. What is CW? CW is the wind force coefficient. And the wind force coefficient is introduced as a safety factor, which we increase if we want to stay on the safe side. And the suggested value is, if I well remember, 1.2, but let me check, because I don't want to say something different with respect to the website. 1 second. And the website is here. Yeah, it's here. But this is port planning. 1 second. I think I have already one open, but I can't find it. So here it is, CW. You see here for wind 1.3, and it can also be less than 1. We will see the conditions, but let's read here, which is better. Okay, depends on the main feature conditioning this coefficient is the direction of the wind. So for isolated ships, isolated means that they are fully exposed to wind, and wind that is crosswise to the ship. It means against the side, it's 1.3. And if the wind is against the bow, against the bow, you understand it's an easier situation because against the bow, the surface is, the wind is split along the two sides. So they recommend CW 0.9, which means a reduction factor. And for wind against the stern is 0.8, okay? Good, now let's go back to here. So CW is a multiplier then. It's a multiplier of what we compute. The rest of the formula is actually physically based. So CW is an empirical coefficient, but the rest of the formula is physically based, and it is based on the computation of the pressure given by the wind against an area. So this is, if you have some memory of physics, of your study of physics, in order to understand the pressure of a fluid, so the pressure of air, for instance, or the pressure of water against a surface, there is a physical relationship to compute it. And this pressure is proportional to the square of velocity, as you may remember. As we know, because we say that when we drive a car, for instance, the resistance of the air is proportional to the square of velocity. So this is why we say, if we want to save fuel, we have to reduce the velocity because the gain that we get is proportional to the square of the reduction of the velocity. So it's what we expect from this formula is that the pressure that we get, it's 1 second, okay. The pressure is proportional to the area, but it's also proportional to the square of the velocity. Good. Now, so CW multiplies times, okay, the side area and the front area of the ship. I mean, the wind can push the ship by pushing on the side area, pushing on the front area, which means the cross area, depending on the direction of the wind. And of course, if the wind is perpendicular to the longitudinal direction of the ship, so perpendicular to the side area, you have pressure only over the side area, and in the front area you don't have any pressure. If the wind blows along the longitudinal direction, it only pushes on the front area, the cross area of the ship, and no pressure is exerted, is given on the side area. If the wind is inclined at an angle, you have a push over both the side area and the front area with the respective component of the forcing. So we expect that the computation of the area exposed to wind depends on the angle of the wind. And this is what you see there, because you see that there is here first the side area, AW, correct? Yes. Times the fraction of the wind on the side area, which depends on the angle. And it's given by sin square of the angle phi. The symbol is phi. Yeah, it's phi. Plus now the component along the front area, which we multiply times cos square of phi. And that's it, I would say. Let me see if I made everything correct. Yes. In this way, we get the area projected in a plane that is perpendicular to the wind direction. And the computation follows from simple trigonometric applications, simple application of trigonometric functions. So when we get the, first of all, AW is larger than BW. Okay, AW is side area of the ship, it's large. Okay, so when do we get the most critical situation. So first of all, the angle phi, if this is the longitudinal direction of the ship, and the ship is, so this one, okay. If this is my ship seen from above, and this is the longitudinal direction of the ship, the angle phi is this one, and this is wind. Let's suppose that this is wind. Okay, this is the angle phi. Okay, so when we reach the most critical condition, when the wind is blowing perpendicular to the longitudinal direction, this is the most unfavorable condition here. Okay, so the most unfavorable condition is at 190 degrees. In this way, you get that this parenthesis converges to the value of AW. Sin square phi is 1, cos square phi is 0. So this is the most critical situation. And it's also understandable, we get it. Okay. So of course the preferable situation is phi equals 0, because we get no component along the AW. We maximize BW, but BW is much lower than AW. And therefore, if we get phi equals 0, we get the full of BW, but still the major component is AW that we bring to 0. This is the most critical situation, I anticipate. Okay, so far we only computed the area. Now, given that PW is a force, we have to multiply area by the pressure of air. The pressure of air, which is 0 for velocity of the wind equals 0, and depends on the square the velocity of the wind. So what follows here is times the pressure of the air. Okay, let me remove the sketch of the ship, okay, because I need room over the blackboard. Okay, good. Now, pressure of air depends on the density of air, gamma W. This is a physical property of air, and I give you the value, but you don't have to remember it. It's much lower. I think it is about 1 over 1,000 or 1 over 100, something like that. We will see, it depends on the units, of course. And then we have the square of the velocity, BW squared divided by 2G. And this one here is the pressure. So this one, this is the pressure. I think I didn't forget anything. Perfect. So in the most critical condition, let's call it PW critical. PW critical. I get the forcing given by CW, AW, and the pressure let's call it here, because I didn't make a nice choice of symbols, because P and P, it's not very clear, but I hope you understand. This is pressure, sine area, CW, which is an empirical coefficient. Basically, you see the physical basis of the formula. The pressure is computed with the application of a physical formula, and pressure times area, and an empirical coefficient. Given that we introduced an empirical coefficient, we say that it's an empirical formula. But an empirical formula with a strong physical basis. Okay. Now, here you can see on the slide, it's specific gravity of air. It's, sorry, I think I said specific density. It's a specific gravity, actually. It's not really a density. It's a force, okay? It's a weight. And it's the weight of air, specific weight of air in units of kilonewton per cubic meters. And in this with these units, kilonewton per cubic meters, it's a specific weight, and it's about 1/100, 0.01. And if you want more digits, see there. VW is the wind velocity we talked about, and 30-second average wind velocity with a gust factor of 1.2. And acceleration of gravity, we know what is. Okay, so this is quite, simple. I ask you kindly to remember it by memory, and I understand that it's something boring, but it's one of the few formulas that I will ask you to learn by memory in the full course. So I think 2-3 max. Okay, but this one is important because it is also similar to the other empirical formulations that we use with the waves, wave forcing, currents, etc. So here is the sketch of the ship. It's the longitudinal axis is also called the ship center line. If you, of course, if you place it in the center of the ship, meaning that it's like an axis of symmetry. And then wind forcing, the angle phi is what is indicated there. And you see the typical position of mooring lines. As I said before, 2 perpendicular lines and other lines with the specific names. So we have terms to identify each one of these, which we will see. Okay, good. Let me check if I'm not forgetting anything here. I check on here. Okay. Okay, there is something more that I want to say here. Let me check in the presentation if I have a slide. Focus, yeah, it's here. Okay, we can use the slides. So AW and BW are features of the ship. So basically, if you know a specific ship, a specific design ship, you can get this information, AW and BW, from the producer, from the technical features and the technical details of the ship. In case you don't have a specific reference, a specific ship to refer to, we have empirical formulas for computing reference values for AW and BW, depending on the beam of the ship, which is relevant for the cross area, and the length between perpendiculars, which is the reference for the side area. Clearly, you can understand this. It's obvious, and depending on a couple of coefficients, of 3 coefficients, G, Z, and Y. So AW, you can express it as the product of the length between perpendiculars and the 2 coefficients, G and Z. So G is just 1 second, because here there are a couple of links that were copied and pasted, which make what is written there not clear. So it's for some reason the link is not. Let me check why. Let me just give me 1 second. I don't understand why. I think this is a. Let me show you the link. This is just a mere mistake. I need to correct it. I have to remember. Okay, so the freeboard. The freeboard, we already know what is. It's the part of the ship, it's F here in this figure. It's the distance between the deck of the ship and the waterline. So basically, G is the ship's freeboard, okay, and Y and Z are mean height of the transverse and the longitudinal area, respectively, of the ship superstructure above deck. So it's if you take the structure of the ship above the deck and you compute the height and the mean height of the transverse and longitudinal area, you can compute, basically this is the height and it's the height of the part of the ship that is above the deck, okay? And these are the two Y and Z. So basically what you get is two empirical formulas that you don't have to remember to estimate AW and BW, okay? We already discussed that the most critical situation is given by phi 90 degrees, wind perpendicular, and the pressure in this equation that is also written over the blackboard is expressed by the multiplication of the air specific weight times the square of the wind velocity divided by 2g. In this graph here, you can see the progress of wind pressure computed with this formulation here. You see that it only depends if you consider the density, the specific weight of the air fixed. It only depends on the square of the wind velocity VW. And therefore you can make a graph with the wind pressure on the horizontal axis and the wind speed over the vertical axis. And depending on the gust factor, if you introduce the gust factor, you get the lower line, the lower black line, which gives an higher pressure for the same wind speed, of course, because you multiply the other line, the upper one, by 1.2. And the upper line is the mere computation of the wind pressure alone. And you get the progress here. And the nice feature here of this graph is that you get here a correspondence with the Beaufort scale. On the right vertical axis, you have the Beaufort scale. And there is here a reference to, there is here a note that here the velocity, the wind speed, look at the vertical axis, is taken at 10 meters above flat terrain, and it is referred to a 10-minute average duration. Why 10 minutes? Because to make the correspondence with the Beaufort scale. The Beaufort scale is, as you may remember, refers to the wind velocity at 10 meters above the ground and 10 minutes duration. So in order to make this correspondence, we refer also for the velocity at these two conditions. And you get this relationship. This doesn't tell you anything more with respect to the analytical formulation. It's just to give you a graphical representation. So if you take a wind velocity of 30 with a gust factor of 1.2, the pressure that we get is about 0.8 kilonewton per square meter. If you multiply by the wind edge area, the side area of the ship, to get the most critical condition, you get a considerable force. It's really considerable. Okay, I think that for what concerns the, let's call it theoretical discussion, we can stop here. What we have now in our background is this formula, which allows us also to start making some exercise. And indeed, I wanted to get this relationship completed also because now I want to focus on the development into R of this formula. It is quite simple. It's a simple computation, okay? And so I propose that we have now about half an hour, 35 minutes. And I propose that we open an R window and try to make this simple application. And without using RStudio for now, okay? It's not necessary. We have half an hour and let's make the simple application of computation. This is the part of a more complete exercise which I wanna present to you now. Do you have any questions, Far? It is quite boring, this part of studying an empirical relationship, and just be patient because I hope it becomes less boring when we make the computation in practice. Okay, good. Okay, so let me first refer to the exercise, which is here. In the links for exercises, you have a short introduction to R and RStudio, which you may look at, but I don't think that we need to look at it together because it's something that I prefer to make in an interactive way. So I prefer to make this short introduction by working possibly together. And then we have another exercise, computation of wind actions on a moored ship and computation of mooring forces. So let's look at this web page. It is much interesting because basically look at the graph. It's a ship that is moored, and we assume that there is a wind blowing perpendicular to the ship center line and in the direction that tends to bring the ships out in the sea. Of course, this is the situation where we get the mooring forces in the form of pulls, you know. And so we assume, as I said, that the wind is blowing perpendicularly to the longitudinal direction, which means that it's the most critical situation, but it is also easier because the computation is it's simple. And the exercise is a bit articulated because besides the computation of the wind force, it is also required that we split it along the mooring lines. Not all of them, actually. We only consider, I think, the red ones. I'm not sure, I need to read. But I reduced the number of mooring lines because otherwise it becomes too complicated. I anticipate that splitting the wind force along the mooring lines is a classical exercise of structural mechanics. So you have basically a force to be split in several components, and it's classical, but the exercise also has to take into account the elasticity of the ropes, which is something a little bit complicated than a static situation, a fully static situation where you have a mere split of one force along given directions. Here you have also to take into account elasticity. So it's a little bit more complicated, but it's still an exercise of structural mechanics. We will not look into the theory of it. I will give you the code, and I will tell you how the code works in terms of the composition. But of course, it's not our job to look into the theory, which is the composition of a force along given elastic directions. It's not our job. So basically, we will take it for granted, okay? But the first step is the computation of the wind force. So let's see here the data. The ship has a displacement of 3,000 tons. It's not really a big displacement. And so what kind of mooring forces are we expecting? If you remember, for 20,000 tons, the mooring forcing were between 10 and 100 tons, the horizontal pull. So here it's 3,000. So I am expecting something between 1.5 to, let's say, 15. This is my expected range of mooring forces, tons, 1.5, 15 tons. So the ship has a waterline length of 117 meters, a draft of 5 meters, a beam of 12 meters, and here is the location of the pivot points. And sorry, of the pivot point. The pivot point is the point in the body of the ship. Let me refer here. This is the pivot point. Imagine that you have a vertical axis that passes through the pivot point. The vertical axis is through the pivot point is the natural axis of rotation of the ship. So if the ship is free to rotate under pressure, a side pressure, it rotates around the pivot point, okay? And here there is the position of the pivot point and the mooring line. Okay, now the data that are interesting to us. It is subjected to an extreme wind velocity of 50 knots, about 100 kilometers per hour. Precisely speaking, rigorously speaking, is 92.6 kilometers per hour. With the wind direction phi is 90 degrees. The ship is moored with mooring lines. Okay, let's forget about the mooring lines. Now we assume CW equal 1.3 and mooring lines, let's forget about the assumption. I am missing the windage area. Let me see. Okay, it's here. A side projected area of 950 square meters. So we have enough. Okay, we have enough because if you remember this equation here, we have CW, we have AW, and we have the wind velocity. So we can compute everything. So let's compute it, okay? Now, let's open an R window. So I am in Windows actually, so I can do that easily. Let me just check how I can get to. Okay, here we are. Okay, here we are. Let me increase the font. Oh, sorry. Okay. Okay, let's write, first of all, let's give the number here, okay? So AW is equal 950, if I well remember. And VW is equal to, just 1 second, because I don't remember. So it's 92.6 kilometers per hour. Okay, I think that it's better if we transform in meters per second. So it's 92.6 kilometers per hour. So let's divide by 1,000. And so we get, sorry, let's multiply by 1,000 and we get in meters. And let's divide by 3600, and this should be from hours to second. So VW is equal to, let's see, 25 meters per second, which is reasonable. Okay, just a consideration on what I did. So I made a transformation of units. Keep in mind that transformation of units, when we make it, 90% of the times we make a mistake. It's something that is unbelievably mistaken. So very often we make a mistake there. And therefore it is essential that you make a check. And fortunately, when we make a mistake, usually it's a huge mistake. So you can, if you make a check, you can detect the mistake. So 25 is a reasonable number because, as I told you, if you remember, the numbers are between 22 meters per second of wind velocity, extreme wind velocity, to 30. So here I got 25, it's perfect. But be careful. And sometimes with other students, not with students in Harbour engineering, I give an exercise of unit transformation. And it is really, in most of the cases, we make a mistake. And myself, I have to be very careful. So in your profession, make sure that you don't make big mistakes. And as I said, big mistakes have the advantage that they are easy to test. They are easy to detect. Okay? So be careful. So this is what we need, and we need the air density. So let's call it AD. And this is equal to, 1 second, I think it was in the presentation. But it's here, 0.01225. 0.01225. And this is kilonewton per cubic meter. But it is fine. I am working with everything in the international system here. So the area is in square meters, which is fine. The wind velocity is meter per second, which is international system. And this one is kilonewton per cubic meters. It's international system. I think it is everything that I need. CW. CW is equal to 1.3. And let's also fix phi. This is equal to half pi, I think. 90 degrees is half pi. So I think pi in R should be written as PE. Let me see, PE. Yeah, okay. So phi is half pi. You see that pi is memorized, it's in the memory of R. So I fixed the phi is half pi, which is okay. Now we have everything. And let's apply the entire formula. Let me clear the screen, okay? And let me just put again on the screen all the definition of the variables. Look, I go back to previous instructions with the arrow up. Okay, arrow up allows me to navigate the memory of R. I want to put on the screen again the previous instruction. Okay, so everything remains there after clearing the screen. And then phi, I need phi. Okay. And now let's compute PW. Okay, PW is equal to CW. If you CW, I forgot to put it here. Sorry, CW. Okay, and now PW is equal to CW. If you want in a formula to get the name of a variable, it is just enough that on the keyboard you put the first letter, and beware that it is case sensitive. So I put a capital C, and then you push the tab. And the tab doesn't give any result, a simple tab, 2 tabs. And you see that you can see CW in the bottom. So let me put CW there.
How do you do this?
Yeah, I show you again. And let me just use phi, you put the first two letters and then the tab. And if one tab doesn't show you anything, two tabs. And you see that it gives to you two alternatives, pi and piper. Piper is a function of R. And we don't know functions yet. Let's forget it. But what I just wanted to show you is that if you push the tab, it can complete the name of the variable. The tab is this key here. And okay. Now let me write PW is equal to CW. If I put only the C as first letter, you see that I have several alternatives. So let's put CW here, okay, times, open parentheses, AW per times sin, I think, okay, let's see, sin phi squared. I prefer to put a parenthesis here because I'm not sure what is the priority between the computation of the function and the elevation at the power, okay? And I didn't define BW, so, but let me write the formula anyway, okay? Plus BW, which is not yet defined, so I will get an error, but let me write it anyway. BW times cos P squared. Yes. Yes, I am okay with the parentheses. And then I can close the second parenthesis times gamma W. Gamma W is AD times wind velocity. It's not here, so I'm not sure if I already defined it. Let me put here VW squared, oops, sorry, squared divided by 2 divided by 9.81. I think it should work here. The only thing is that when I type enter, I will get an error because BW is not defined. You see? Object BW not found. So it means that VW was defined. Let me check it. Yes, it's here. VW was already defined. Now let's put any number for BW because it's not, doesn't matter because it's multiplied by 0. So let me put here 10, okay? And then I can go back with the arrow up and compute it again. And now I got the result. What is the result? PW is 510 kilonewton, no, or Newton. Just 1 second because I need to think of it. The unit I need to think of it. So it is Newton. So the gravity is in Newton. I think this is Newton per square meter. Let me check the result on the website. Ah, sorry, because it's not per square meter. This is correct. This is the force, and therefore it's kilonewton. It's kilonewton because the density of air is in kilonewton. Yes, it's kilonewton. Okay, because the density of air is in kilonewton. So the result is also in kilonewton. This was relatively simple, but it allowed us to get a little bit more acquainted with computations in R. Now, let's save it, okay? Because at this stage, given that we don't finish this exercise today, we finish next time, let's save it, okay? And there are two things to be saved: the variables that I defined, the result, and the history, the previous instructions. First of all, the variables, you can see them if you type list, ls, you see the variables. So how to save the variables? Save image. Save image with a dot. You see, I didn't remember the name of the function. So I typed save tab. I didn't get any result with the tab. So I said, oh, I made a mistake. So I put the dot here, tab, save image. Double parentheses, I save the image. And now I have to save the history, okay? Save again. And see here the alternatives, save history. Okay, and keep in mind, if you have Mac, one of these two is using a different instruction. Find it with the tab. Just type save and then double tab, and you see the instructions. I think it is save history that it's a bit different. Yeah. No, you see that I wrote PW. I recalled it. You see that I do it again. Okay. This is the computation of the formula, no result. But then I can just type PW. Yeah, correct.
After this formula, if you press go on, there is a plus.
Because you forgot a parenthesis. For sure. And if you need to correct it, you can just make type a second parenthesis first after the plus and press enter. And then you may get a mistake or an error or something.
Yeah.
Okay, so go with the arrow up to correct the formula by placing the parentheses in the right place. Because if you got an error, it means that the parenthesis that was missing was not just the last one. Just check and compare with my result if you missed the parenthesis. BW, okay. But there is another, okay, there are two issues here. BW has to be defined, and you see that I defined it by 10. And the second issue is the missing parenthesis, because if you placed it at the end of the formula, it's not the correct position. So you have to retype the formula and place the parenthesis in the correct position. It's still on the screen, so you have to find. This is another issue, which is, I mean, interesting. When you use parentheses, be careful, because very often we forget to close them. When we will use the editor, you will see that the editor helps you in that respect, because when you open a parenthesis, the editor closes also the parenthesis. So it shows to you two parentheses, and you have to write in between. And also, usually the editor displays the parentheses with different colors so that you can see the couples of parentheses in a long relationship. And this is an help. In any case, when you use parentheses in coding, be very careful, because, you know, it is another very frequent mistake. Sometimes you don't see the mistake, because if you misplaced it, you forget, you put the parentheses in a position that is not correct. You don't see the mistake. The program just says, okay, that's fine, I made the computation, but check the result. In general, when you use a code, no matter if the code was written by you or by others, try to check the result anytime that you can, okay?
You have seen that I checked in my website because I knew that there was the result there. I wanted to check whether I made a mistake here because it is, you have to use anyway, any means. And of course, my position was easy because I had already made this computation before and I checked it with the previous computation. But you have several means to check the correctness of a result. So don't forget to make frequent checks. Now, we saved, as I said, there is another way to save everything, which is very convenient, which is you close R with quit, the function Q, and then you see, do you want to save? And so don't forget to say yes. And be careful of two things. First, in R, you don't have undo. You cannot make any undo. This opportunity in R is given by the history. So clearly, if you make a mistake that you cannot undo, you have in memory all the past instruction. You can repeat what you have done very easily. So this is a way to undo. Also, I think in MATLAB it's the same. Second thing, when you close a window and you don't save, there is no way to recover what you have lost. Okay, same in Office, in Excel. When you close, and do you want to save? No, there is no way to recover it. Don't forget this. And this is particularly important because sometimes it may happen that the computer crashes. After a crash, if you didn't save, you are lost. And this happens very frequently. It happens to me at least once a week that I say, okay, I will save later, and then crash. I mean, try not to get trapped into these mistakes. Finally, I closed R. Let me start it again because I want you to see that what you get when you start it again. So 1 second, okay. R. So if I go back with the arrow up, do you see? I have everything there. The history was saved. If I make a list, ls, everything was saved. Okay, the next question could be, where did it save everything? Let's forget about this for now, okay? Somewhere it is there, somewhere, and you can recover it. And then let's forget about the details that will follow. Now, there is another thing that I want, I have like 5 minutes, so let me go out from here. This year, I decided, finally, to, after thinking of it a lot, to introduce you, besides R, also Python. Do you have any experience in Python? Raise your hand. No, okay. This is interesting because I also have very limited experience in Python, but I am realizing that it's increasing the popularity. The popularity of Python is dramatically increasing, and also the performances in terms of graphical output, of flexibility. I mean, they are really astonishing. I have my PhD students that have no doubt. They use both, all of them, MATLAB, R, Python, and they told me, look, for some applications, Python cannot be, it's the best, definitely, by far. So I decided, indeed, I had also past students. Last year, I had a student in Harbour engineering, and he said, why are you still using R? You need to use Python. And he gave to me a Python program for computing something. So I think that it's time that we also start Python. And we are starting R from scratch. Let's also start Python from scratch, okay? And it is, I mean, I think it is a nice addition to your CV. So let's, how to make it. I said, I have limited experience, but I looked for something. So first of all, let's look for Python, and Python here, Python download, okay? The first thing, we have to install it. First, probably you have already it. So if you are a Mac user, maybe that you have already it. In this application of Windows, in this version of Windows, it was not there, and I had to install it. And yeah, I already installed it. It is very easy. So what you have to do to install it, let's do this. You go in search for applications in order to see if you have already it. And in search for applications, just write Python. And you see that I found here already the application because I installed it. But if you don't have it, like I didn't when I got here, you find several options for downloading the application. And then you can easily download it and install it. I did it in 5 minutes. And of course, I cannot redo it because it's already there. And take the first version that you find and install it. And if you start it, you should get something like this, which is like an R console. It is similar. So we don't start today. I just wanted to kindly ask you, install it on your PC. And next time we will repeat the same computation in Python. I tell you, I anticipate to you, very easy. So if I write AW equal to 1950, I get it. And if I make AW times 2, that's it. So it is very similar, at least for these trivial computations. So let's start, okay? And then we will move forward in parallel, R and Python. I think, do you have any question? Okay, let me just break the screen sharing and let me close the recording.